Kia ora team. Why does the ECG with hyperkalemia look like someone's grabbed it and kind of stretched it out and made it longer? So let's start at the beginning. Our cell membrane is like a salty banana. So this means we've got more potassium on the inside and more sodium on the outside. How it's maintained is with our sodium-potassium pump. So we got this little pump that's run on an ATP and it shoots out 3 sodium to 2 potassium. This means that there's more positive things leaving the cell than entering. So therefore the inside of the cell is going to be negative, which means polarized. We also have potassium channels, which cause potassium to leak out, which is going to make positive things leaking out, makes the inside even more negative. Awesome. So what happens with hyperkalemia? Hyper, more than, K, potassium, more potassium in the emia, blood. So with the cell, it's always going to have more potassium than outside the cell. But in hyperkalemia, the level of potassium is higher than normal. If the level of potassium outside the cell is higher than the inside, you're dead. With hyperkalemia, you imagine like an avalanche. Normally the inside of the cell has lots more potassium than the outside. So if you think of an avalanche, if we've got the steep gradient, all the snow is going to fall quickly down the hill. With hyperkalemia, it's like that slope is less. The amount inside the cell is still higher, but now we've got more potassium outside the cell. So if we have an avalanche, it's going to trickle down the hill instead of crashing down the hill. That's our concentration gradient. Now, if we look at our cardiac myocyte action potential, the resting membrane is nice and negative because of what we talked about before. Then the message comes in to contract. So we get calcium and sodium coming in through the gap junctions, and slowly the cell becomes slightly more positive until it hits a threshold, and then sodium channels open and we shoot up until we get positive. Then chloride enters, which is negative, and potassium starts leaving, and this is going to make us start to come down a bit, so approaching 0 instead of being positive. And now we get calcium coming in and potassium going out. So this is that plateau phase. So during this plateau phase, calcium coming in, potassium going out, they're both positive, so that's why the electrical current doesn't change that much. Now in hyperkalemia, if we've got lots of potassium on the outside, then we don't have as much force driving the avalanche of potassium to leave the cell. So it's going to take a little bit longer for potassium to drive out because of that concentration gradient. So during this phase, we're slowly going to be getting more and more negative. But if we can't get potassium out as fast, it's going to take longer for that cell to become negative. So that's why our QRS complex, when the ventricle contracts, that's going to become widened because it's harder to get potassium leaving the cell. And then as we finally get to around neutral 0-ish, we get more potassium channels opening. So potassium leaves in greater numbers, and then we get that depolarizing again until we're back at the resting membrane. Again, even if these potassium channels open, if there's lots of potassium on the outside, it means there's less reason for potassium to rush out and avalanche out of the cell. So therefore it's going to take longer. So that's why as we get more and more hyperkalemia, these segments on our ECG are going to get longer and wider and wider and wider. Okay, happy studying, team.